Okay, so we have this problem. It's a GATE 2019, so and problem number 3. It's a worth 1 mark. So you have given a complex function, complex valued function from C now, and defined by f of x y is this and this, and f prime z is usual derivative of f. Then we have to say at what point, like there are some points, and we have to see that whether f is the function, the given function is analytic or differentiable or not. So yes. So see, whenever we have a function asking about analyticity or differentiability, so first thing that we should check is Cauchy-Riemann equation. So it says that if f is a function like uxy, where z is x plus iy plus iota times vxy, where u and v are both real valued function, then this says the Cauchy-Riemann equation says that the x derivative of u is equals to the y derivative of v, and the y derivative of u is equals to minus v derivative of x. So this set of equation is called CR equation or Cauchy-Riemann equation. So we have a theorem here that says that so if a function is analytic, so analytic implies Cauchy-Riemann equation. But the converse is not true. So this converse is not true. Okay, and but in certain cases the converse is also true. So if this the partials, if the partials are continuous, okay, and it then there satisfies this Cauchy-Riemann, and they satisfy, let's say 1, then the function f is analytic. And all those things are working in a domain. Okay, so I'm talking about in a domain, because analytic, like whenever we talk about analyticity, we say that like a function is analytic at a point x if there exists a neighborhood around x where the function is differentiable. Okay, so let's check now. So yeah, so we have our u is this and v is this. So let's uxy is x cube plus 3xy square, and vxy is equals to y cube plus 3x square y. Okay, now let's compute the x and y derivative of u and v. So the x derivative of u will be 3x square plus 3y square, and y derivative of u will be only 3 and 6, so it's 6xy. And what is the x derivative of v, that will be 6xy, and the y derivative of v will be 3y square plus 3x square. So observe that here we have ux equals to vy. So for every xy, it's in c, so I'm writing xy means x plus iota y. C ux is equals to vy, but now we also need that uy should equals to minus of vx. So uy should equals to minus vx. This says that, so this is true. This, so the ui is equals to minus vx. This implies that xy is equals to 0. This implies that either x equals to 0 or y equals to 0. So it means that the complex number will be either purely real or purely imaginary. Then only the Cauchy-Riemann equations are satisfied. Okay. So it means that, so and now we also know a function is differentiable at z if it satisfies the Cauchy-Riemann equation at that point z. Okay. So a function f is differentiable at z0 if it satisfies, and basically it's if and only if it satisfies the Cauchy-Riemann equations at, okay. So yes, so from this all this argument, option A is wrong, and of course f is differentiable at I because it's a purely imaginary. This is wrong and this is true. Now why this is wrong? F is analytic at origin. So what do you mean by analyticity at origin? So analyticity at origin means it will be differentiable in a neighborhood of 0. Okay, but if you consider any small neighborhood, any neighborhood of 0, because analyticity at the origin means, so this means there exists a neighborhood of 0 such that f is differentiable on that neighborhood. But here, however small neighborhood you choose, however small it will contain the points which are neither purely real nor purely imaginary, and hence the function will not be differentiable, and that is why the function is not analytic at the origin. Okay, so this option also ruled out. So we have the correct answer, which is differentiable at 1. Okay, thank you.